In the previous lecture, we discussed in depth about the coupled line directional coupler, and we had ended that lecture by discussing what is the transmission coefficient and the coupling coefficient. In other words, what is the S21 and S31 as functions of the electrical length theta. In this case, theta indicates the length or the electrical length over which the pair of conductors are running in close proximity to each other. So we had essentially taken three cases having three different combinations of Z0E and Z0O, that is the even and odd mode characteristic impedances, and we had said that the geometric mean will be equal to 50 ohms. That was the criteria we had put, because that is, as we had derived, a necessary criteria to achieve matching at all ports as well as isolation between the ports 1 and 4. So the coupled line coupler is a reciprocal device. If something is happening from one side, the similar thing will happen from other side also. So just to make things clear, this is port 1, this is port 2, port 3 and port 4. And this length, this electrical length is theta. So with respect to port 1, if the input is at port 1, port 3 will be the coupled port, port 4 will be the isolated port. Likewise, if the input is at port 2, port 3 will be isolated with respect to port 2 and port 4 will be the coupled port with respect to port 2. So coming back to those three cases that we had discussed in the previous lecture. So we had said that, case 1 is when Z0E was 86.73 ohms and Z0O was 28.83 ohms. Case 2 was when Z0E is 69.37 ohms and Z0O is 36.04 ohms. And case number 3 was when Z0E was 59.84 ohms and Z0O is 41.78 ohms. For all of these three cases, Z0 is the geometric mean of the Z0E and Z0O, and that you can verify is 50 ohms. So we had said that if we are plotting the coupling S31 in dB, the magnitude of S31 in dB with respect to theta, and we can also do the plot of the transmission coefficient mod S21 in dB as a function of theta. So we had seen that the curves were something like this. So the first case, case 1, when the peak was happening at minus 6 dB. In case 2, this one, it would be something like this. This is minus 10 dB. And the third case is something like this. Where the peak is around minus 15 dB and the peak is achieved at theta equals pi by 2. Likewise, as an extension of this, we can try to plot S21 also in dB as a function of theta, because S31 and S21 we had derived both quantities as functions of theta. So Again, something very interesting we will notice. Suppose this is 0. What you will notice is, for case 1, you will see something like this. So the minima you will get at pi by 2, and the value of that minima is minus 1.25 dB. For case number 2, over here, let's mark it over here. This is case number 1. For case number 2, the minima will now be at a higher value, and this one comes out to be minus 0.46 dB. And then for case 3, it comes out to be something like this. The minima is about minus 0.14 dB. We can actually verify that from the expressions for S31 and S21 that we had derived in the previous lecture, we can indeed achieve maximas or minimas at theta equals pi by 2. So let us quickly write what those expressions were. Let us say S31 was j sine theta times Z0e by Z0o root minus Z0o by Z0e root divided by 2 cos theta plus j sine theta Z0e by Z0o plus Z0e by Z0o. So then if you substitute, if you take the derivative of this S31 with respect to theta, you will see that at theta equals pi by 2, the mod of S31 is essentially this. The cos theta term will disappear, j sin theta and j sin theta will cancel out. So you will see something like this. This will be Z0o by Z0e. Yeah, sorry. This will be Z0e by Z0o. This is what it is. Now, if you just do some little bit of cross multiplication, you will see that what you will get is something like this. The denominators will be common, so they'll cancel out. Z0e root and Z0e root will become Z0e minus Z0o divided by Z0e plus Z0o. So this is the maximum possible value of S31. So this is called as the peak coupling coefficient. That is C. So what we can define is that C is equal to this. As a converse, you can also prove that C can be related using Z0 also. As a converse of this, I leave it to you as an exercise, which is a pretty easy exercise. That is, you can also achieve Z0e as a function of C. That is this. And Z0o will be Z0 times this. These two are converses, these two are consequences of this expression. So these will be useful for you to know in case you are dealing with problems related to coupled line couplers. Likewise, if I now describe the expression for S21, we had derived that S21 was something like this. So at theta equal to pi by 2, what will happen is that this cos theta term will disappear and this will become 1. So mod of S21 would now become 2 by this j term will also go, that is under root so if you now simplify this, what you will get is the following. I think this should be it. Yes, so this is the minimum transmission coefficient. When S31 increases, S21 decreases. Why? Because S11 and S41 are 0. This comes as a consequence of the unitary property which we had discussed. So suppose the S parameter matrix of this coupler looks something like this: S11, S12, S13, S14, and likewise. So if I now take the S transpose times the S conjugate, for the unitary property, and if I multiply the first row of S transpose and the first column of H conjugate, what I will get is this. That is equal to 1. So what we already know from our discussion on the coupled line coupler is that S11 and S41 are always 0. So that means all we need is mod S21 square plus mod S31 square will be equal to 1. So therefore, what we see is that if you increase S21 in case 1, if you increase the S31, the S21 reduces. And if you decrease the S31, the S21 increases. So therefore, it is again indicative of a trade-off. It is again indicative of a trade-off. The more power you couple to the second conductor, less is the power that reaches the other port of the main conductor, and less is the power coupled to the second conductor, more is the power that reaches port 2 of the first main conductor. So that is something very important to know. This is a consequence of the unitary property, and that is a consequence of the law of conservation of power. Now, again, let us go back to those three cases. Case 1, where Z0E was 86.73 ohms and Z0O was 28.83 ohms. Case 2 is when Z0E is 69.37 ohms and Z0O is 36.04 ohms. and case 3 is when Z0E is 59.84 ohms and Z0O is 41.78 ohms. Once again, Z0 is 50 ohms for all of these three cases because it is the geometric mean of both of these even and odd mode impedances. Now, much like how we had described in the earlier part of this course that the dimensions of the conductor play a very important role in determining the characteristic impedance of any form of a transmission line like microstrip line, strip line or coaxial cable or anything for that matter. So suppose we try to realize these coupled structures in microstrip. Coupled line microstrip structures. So over here we can take the three cases independently. There exist formulae also which will help you find out the width, the length and so on. So we have not discussed too much about the length of the line, we just left it as theta. But suppose we want to obtain the maximum possible coupling for each case. Then we know that theta equals pi by 2 is when maximum coupling occurs. We have just discussed that. And we know that theta equals to pi by 2 also corresponds to the physical length of lambda by 4. This is coming back time and again to remind us that lambda by 4 somehow has a very significant value. It has a very significant effect in the broad domain of RF. While it is not a determinant in saying that S11 or S41 cannot be 0, because we have proved that as long as the Z0 is the geometric mean of the Z0E and Z0O, the S11 and S41 will always be 0 and it will not be a function of length. But the coupling and the S21, they are indeed functions of theta. So therefore we cannot totally write this away. So for the first case, where, or let us say we'll start from the third case, Z0E and Z0O are 59.84 and 41.78. Then in that case, we can define the quantities. L is the length of the conductor, each of this is the width W, and then we will also define something called gap or G, the gap between the conductors. So for case 3, what we are seeing is for 59.84 ohms of Z0E and Z0O of 41.78, the calculator using those big microstrip line formulae, which is not of prime importance, what we get is that for case 3, the width W of each conductor is 2.9 millimeters. The length is 23.13 millimeters, lambda by 4. So this is for a frequency of, let us say, 1.8 gigahertz. All what I'm going to show are for dimensions. The dimensions are calculated for frequency of 1.8 gigahertz at this length. At the same frequency, this length corresponds to lambda by 4. And the gap between the two conductors is seen to be 0.98 millimeters. That means it can achieve a peak coupling of minus 15 dB, as we had seen from the graph. Third case, we can achieve a peak coupling of minus 15 dB if the two conductors are spaced by 0.98 millimeters or almost 1 millimeter. In case 2, we could achieve a maximum coupling of minus 10 dB And in case 1, we could achieve a maximum of minus 60. Let us now see what those dimensions would be. So my calculator in the computer throws me these values for case number 2. The width of each strip would be 2.55 millimeters. The length would be 23.45 millimeters. And the gap between the two conductors would be 0.29 millimeters, which is very, 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 very small, which further reiterates that for more coupling to take place, the proximity of the conductors must be more. And in the first case, what we get, each strip width is 1.91 millimeters. The length is 23.8 millimeters. And the gap, now things get interesting. The gap is 42 microns or 42 micrometers. That is 0.042 millimeters. It is now reduced by a very, very large factor. That means if you want to achieve 6 dB coupling or minus 6 dB S31, the gap between the two conductors has to be as small as 42 micrometers. Now all of these are for epsilon r equals 4.4 substrate and the substrate height is 1.6 millimeters. Same variables which we had taken for microstrip. So what we are seeing, the gap is reducing between the two conductors. So if I am going left, that means coupling becomes stronger. And if I go right, coupling becomes weaker. Coupling becomes stronger and at the same time, the mod of S21 reduces. And here the mod of S21 increases to satisfy the unitary property. So what we are seeing once again is that for strong coupling to take place, the gap between the lines must be really small. Must be really small. Now it may be so small, this 42 microns, that on a printed circuit board it might be very difficult to realize. It might be very difficult to realize. So therefore we can say just by this analysis that by nature coupled line couplers are weak couplers, because it is very difficult in practice to achieve strong coupling. So coupled line directional couplers in practice, their coupling levels are rather weak. So with some difficulty you can achieve minus 10 dB, but anything above that is difficult. So minus 10 dB means you are essentially sending 10% of the power as coupled and 90% goes to the port 2. But if I want to send more power to the coupled port, my job becomes difficult. So the next question is, why do we need to send more power to the coupled port? Why do we need stronger coupling? Or why do we need couplers with larger magnitude of S31. Well, what a stronger S31 means is that the power that is entering port 1 of the coupler is getting divided between ports 2 and 3, that is the through port and the coupled port. So therefore, coupling is not just something that we are inducing. We can look at it as a form of power division. So if there is some power P that is entering, and let us say some power comes out of here at port 2, that's P2, and some power comes out of here, that is P3, let us say there is 0 over here, then I can say that P is nothing but the sum of P2 and P3. So we can choose what is the relationship between P2 and P3 by designing our coupler properly. So for coupled line couplers, P2 is usually much more than P3. Here DC means directional coupler. So much more power reaches port 2 as compared to port 3, because there is no direct path over here. One can also ask whether we can enter some power at port 1 and can we achieve half the power going to port 2 and half the power going to port 3. This is extremely difficult, rather I should say impossible, using coupled lines, because the electromagnetic induction just cannot be that strong. The other question is that why do we also want to do such kind of power division? We already have things like the Wilkinson power divider. Well, we do, and Wilkinson power divider is indeed a wonderful device. But aside the fact that it is very useful, we cannot deny that the directional coupler provides us a way to divide power by having a circuit that is matched, that is reciprocal, and at the same time lossless. Because we have proved that it is matched, it can be matched at all ports as long as the Z0, Z0E and Z0O relation is maintained. It is reciprocal by the virtue of its structure, and lossless because it has no resistors whatsoever. So therefore, this gives us a prospect of a lossless power divider also. This gives us the prospect of a lossless power divider, but what we know from our discussion so far is that it is impossible to achieve equal power division between ports 2 and 3 with coupled lines. It is rather not possible. So therefore, the only way to do so is to have some kind of direct path between the two conductors. By doing so, we can send more power to port 3, but at the same time we are losing something out. That is, we are losing the right to call this as a coupler. If we are giving direct paths between the two conductors, then there is no question of coupling. There is no question of any electromagnetic induction happening, because now the paths are there. We don't need to induce current in the second conductor. So therefore, those kind of devices which have direct connections between the two conductors, they are not called couplers usually. They are called as hybrids. while the functionality remains similar, that you can take some wave at some port and you can divide it into two ports while the last port does not get anything. So it is satisfying the definition of a coupler, but it's not really a coupler because there is a direct connection. So then those devices are called as hybrids. Although in literature you will also come across the word coupler, both are used. I prefer the term hybrid more because that's a more better indication of its behavior. It is a power divider as well as a coupler, so we call it hybrid. So therefore, now we introduce the concept of something called as hybrids. Hybrids work this way. Now again, I'm going to draw the diagram using transmission lines. Let us say this is my first conductor. Let's say this is port 1 and this is port 2. Now my second line is over here. So rather than inducing, what we will do is we will connect these two lines by another two transmission lines. So what it looks like is this. One more transmission line over here and another transmission line over here. So again, let us say that the second conductor in each case is grounded. We will now change the definition very slightly. Earlier this was port 3 and this was port 4, but now we will call this as port 3 and this as port 4. The reason for doing so will be very clear soon. Now let us say the characteristic impedance of the top line is Zm, the bottom line is also Zm. The characteristic impedance of this line is ZB and this is also ZB. And the characteristic impedance of the port lines as always is Z0. And the length of each of these is taken as lambda by 4, whether it is this line or this line. Zm, why it is called? Because this is the main line. And the fact that there exists another path between these two main conductors in the form of another transmission line, these are called as branch lines. So therefore this kind of hybrid is called as a branch line hybrid. The first theoretical as well as experimental demonstration of a branch line hybrid was given by an American scientist called John Reed more than 50 years ago. So after that, this has also received considerable attention because this gives us the prospect of a totally lossless power divider that can be matched, that can be lossless, and that can also be reciprocal, because 4-port networks don't have any constraints on the properties that any network can achieve. The idea behind having a branch line hybrid, or some people also call it as a branch line coupler, is to achieve tighter coupling. That is, this can achieve high values of S31 magnitude. because now there is a direct connection between the main lines. Now obviously there are these variables Zm, Zb, Zm, Zb and the characteristic impedance of the feed line Z0. So obviously there is some relation that could be there between these, and these impedances are extremely critical in deciding how much power goes to port 2, how much power goes to port 3. Now suppose we say, can we achieve mod S21 equals mod S31? That's a question. Well, we could achieve this if, let us say, the input is at port 1. We again call port 2 as a through port, port 3 as the coupled port, although there is no actual coupling that's happening, and port 4 is the isolated port. So for isolated port with respect to port 1, there should be no power over here. So therefore, if port 1 is also matched, then this is needed. Then in that case, whatever is the power at port 1, that could possibly get divided equally. So if so, then the mod of S21 and the mod of S31 will be equal to each other, and that is 1 by root 2. But obviously it depends on the impedance values, and we shall see how to work with that also. Now, if S41 and S11 are 0, which we can achieve, all we know is that the magnitudes of S21 and S31 are this. But in general, these are complex quantities. So how can we represent them with their phase parts also? So to do this, again we shall look at the top view only. We will not look at the bottom conductor. Top view of a branch line hybrid. Let us say this is port 1, this is port 2, this is port 4, and this is port 3. So therefore, let us say the impedance of this is Zm, this is Zm, this is Zb, and this is Zb. And the length of each line is lambda by 4. Each line is lambda by 4 long. So, let's get to business. Suppose there is an input at port 1. Let us now look what are the paths possible this wave can take to travel from port 1 to port 2. One direct path is over here through Zm. The other is a longer path. So for the sake of simplicity, I can say the wave would definitely want to take the shorter path. So this is the shortest path. The phase difference that it is introducing going from this point to this point is corresponding to lambda by 4. So the phase is pi by 2. The phase is pi by 2. So then in that case, I can say that S21 will be 1 by root 2 times e raised to minus j pi by 2, Obviously it will be minus because plus phase is not possible. There is some phase delay that's happening. So this will be equal to minus j by root 2. Now what about going from port 1 to port 3? While going from port 1 to port 3, there are two paths it can take. One path is from here, this way. The other path is this way. The other path is this way. So both are equally possible. So irrespective of whichever path it takes, it has to undergo two lines each of length lambda by 4. So therefore in this case the phase difference will be minus pi. The phase delay will be minus pi. So S31 will be the magnitude times e raised to minus j pi, which is nothing but minus 1 by root 2. So indeed it is possible to have this. Although our discussion is still quite superficial, this is indeed possible. If, again, these two are possible, if and only if S11 equals S41 equals 0. So let us say somehow we made S11 a 0, somehow. Then we are still not sure how S41 will be 0. So let us again consider a look at this. And we will look now at the path from port 1 to port 4. In that case, again, so while going from port 1 to port 4, again there are two paths. One path is directly from here to here. The other path is over here. Now, let us play along and consider that both paths are equally likely. And why we are saying that is because somehow we know that we want to make S41 as 0. So therefore, one path alone is not sufficient. Because if there is some input over here, some part of it is bound to reach port 4. So suppose there is an input over here. Let us say input at port 1. Let's say voltage input. Some voltage is there. Let's call it as x of t. It's a time varying function. And we'll call it as V0 cos omega 0 t plus some phase phi. Now what is happening? This signal which is coming to port 1 is passing now through two different paths. So let's call this as path 1 and let's call this as path 2. So due to path 1, the voltage at port 4, obviously there may be some change in magnitude. So let's call it as some x1 of t. That will be V1 cos of omega 0 t plus phi, and also the phase of this lambda by 4, which is minus pi by 2. Likewise, due to path 2, the voltage at port 4, that is for this path, let's call it as x2 of t. Let's say the magnitude has changed and we will call it as cos omega 0 t plus phi minus 90 degrees, 90 degrees, 90 degrees. So it will be 270 degrees or 3 pi by 2. Now you may ask, why the magnitudes are not changing? Why they are no longer V0? It's not because the network is lossy. It is because it is encountering a junction. So the moment it sees a junction, it will split up. At here, it will split up one part here, one part here. Here, it will split up one side, one part this side, one part this side, and so on. So there is very likely going to be some voltage change because there are multiple junctions the wave is facing when it's going from one point to another point. Now, what is ultimately happening is that because of these two paths, because of these two distinct paths, there are two waveforms which are entering port 4, x1 of t and x2 of t. And ultimately, the net voltage at port 4, that is equal to x1 of t plus x2 of t. So these waves will essentially superimpose. Now what we are encountering is this. The two waves are out of phase. The phase over here is pi by 2. Here it is 3 pi by 2. So the phase difference is pi. The phase difference is pi. But now, if the phase difference is pi and somehow we are able to make V1 equal to V2, somehow we are able to make V1 equal to V2, then the two waves will be cancelled out. If and only if V1 equals V2. Since pi phase difference exists. Since the pi phase difference exists. Okay. So now, if V1 equals V2, the net voltage at port 4 can be made 0. So therefore, this means under this condition S41 will be 0, which is doable. Now suppose this is Zm, this is Zm, this is Zb, and this is Zb. Can we try to ensure some relation between Zm and Zb and try and make V1 equals V2? Now, notice that the V1 voltage corresponding to x1 travels a shorter path, whereas the x2 of t or the V2 travels a longer path. So therefore, it is very likely that V1 magnitude will be more than V2. To prevent that, to prevent V1 being much more in magnitude than V2, we will try to make it comparable. So therefore, the impedance of the longer path must be lower and the impedance of the shorter path must be higher. So therefore, to maintain this, we will try to have the branch line impedance as always more than the main line impedance. That is, ZB should be more than ZM. To ensure that V1 and V2 are comparable, otherwise V1 will be much more in magnitude as compared to V2. So therefore, this is an extremely important requirement for the isolation between port 4 and port 1 to exist perfectly. That is, any input at port 1, no portion of it should come to port 4. So in today's lecture, we discussed some drawbacks and some interesting properties, and thereafter the drawbacks of coupled line directional couplers. And their major drawback is that they are essentially loosely coupled lines, and that motivated us to go for the structure called as hybrids, where we can achieve higher values of coupling. We looked at something called as a branch line hybrid, we started the discussion on it, and we saw that in the endeavor to have equal power divisions between ports 2 and 3, that is tight coupling along with equal power division, we have to try and maintain S11 as 0 and S41 as 0. And for that, we need the branch line impedance should be much more than the main line impedance. Is this the only possible relation, or is there something more? That we will look at in more detail in the next lecture. Thank you.